So magnetic flux phi 1 from coil 1 has two components, as we see from the previous lecture, that phi 1 links only coil 1 and phi 2 links both coil, means from 1 and 2. So we can write here phi 1 is equal to phi 1 plus phi 1 2, phi 1 plus phi 1 2, and thus the voltage induced, and the voltage induced in coil 1 is V1 is equal to N1 d phi 1 divided by di1, and we can we can write this equation to yielding that L1, that means the inductance of first coil. Okay, in the next part, the voltage induces in coil 2. That is a very much important part, that the voltage induced, that is not self inductance. If it is self inductance, we should write L. It will be L1, it can be L2. That means that is a self inductance of a coil. But if it is a mutual inductance, that you can see in that part, N2 d phi 1 2 divided by di1, that can be replaced at M21. The subscript 21 in M21 means the mutual inductance on coil 2. So the 2 is on the previous part and 1 is on the later part. So on coil 2 due to coil 1. That means the last subscript recognizes the coil has the inductance due to coil 1. Coil 2 has the inductance due to coil 1. Okay. So as we understand this in that part, that is known as mutual inductance. So again in case 2, here we have to say that in previously we have a case 1, but there are still a case 2, the same circuit, but let current I2 flow in coil 2 in different, the V1 is open now, and the I2 is now just charging, or the I2, the current is now started and open, and it's on circuit. So L2 is a self inductance, L1 is the self inductance of coil 1 with an N1 turns, and L2 is a self inductance of N2 turns. So the mutual inductance will be created between these two. As you can see, there is a line that has been created between these two coils, that is known as mutual inductance, and mutual flux is phi 21. The magnetic flux phi 2 from coil 2 has two components, that is gonna be phi 22 links only coil 2, and phi 21 links both coils, as you can see here. So that is the case 2 condition. So again coming back to the conditions and things, we can write a phi 2 is equal to phi 21 plus phi 22. So thus the voltage induced in coil 2, the voltage induced in coil 2 V2 is equal to N2 d phi 22 divided by di2 and di2 divided by d2, that is previously known. As we know that d phi divided by, if we take dt here, so di here, d phi by dt, so just replace this thing like that, d phi divided by di, and if you take di, so you have to take di through here, so di divided by dt, as that is a part of mathematical calculation, that you take di, as because of these two can be cut off, these two can be cancelled in these through, but to make the N2 d phi di2 to self inductance L2, we have to do it to make the calculation like this. So now the voltage induced in coil 1, here you can see in coil 1 there is no source, there is no current source. Here there is a current source, but there is no current source here, but the flux, the mutual flux has been created due to L2. So we can write mu we can write that that will be M12 like that. Okay, yes, that is M12. Voltage induced in coil 1 is V1 N1 d phi 21 that is the mutual flux, and di2 dt. Now we can say the subscript 12 in M12 means the mutual inductance on coil 1 due to coil 2. That means the mutual inductance is created by coil 2. On the another set, since the two circuits and two currents are same, as you can see, the circuits and currents are same, because just we have just put this through in the first section to the last loop. The two loops has been created. First of all, we have given the current source in L1 loop, then we have given the current source in L2 loop, just vice versa. So we can write M21 is equal to M12 is equal to M. That means mutual inductance M is measured in Henrys, and that is gonna equal, because the circuits two currents are the same. Now the coupling coefficient K. So it is measured of the magnetic coupling between two coils. That means how much power and how much magnetic flux has been coupled or taken over by a coil. Okay, when there is mutual inductance, how much power has been transferred, or how much as you can see that say that how much magnetic flux has been created due to another coil. That is the thing of coupling coefficient, and that is no unit, as it is known as coefficient. So range of K is equal to 0 from 0 to 1. K0 means the two coils are not coupled. If K is equal to 1, that means perfectly coupled. If it's less than 0.5, that means two coils are loosely coupled, and if it's greater than 0.5, that means the two coils are tightly coupled. That means that is a one kind of measurement that how the coupling is strong or not strong, or poorly coupled or not coupled. We can find it out from this coefficient. So again, coming back to the point of K, the K depends on the closeness of two coils, their core and their orientation and their winding. That means K depends on the three parts. That means their core, if it's an iron core or any other alloy core are there, their orientation, that means how many turns the coil has been used, how much diameters the coil has been wounded, and also their winding. The coefficient of coupling K is given by this formula. K is equal to M divided by root over L1 L2. If there are two coils, L1 L2 are the self inductance, and M is the mutual inductance. Mutual inductance is same, divided by root over L1 and L2, and from this we can also find out M is equal to K root over L1 L2. So from there we can also find out the dot determination. The dot determination is required to determine polarity of mutual induced voltage. That means in which polarity the plus and minus are given, a north or south pole has been determined. So a dot is placed in the circuit at one end of each of the two magnetically coupled coils to indicate the direction of the magnetic flux if current enters that dotted terminal of the coil. That means a dot is placed in the circuit at one end of each of the two magnetically coupled coils to indicate the direction of the magnetic flux if the current enters the dotted terminal in the coil. That means to identify the polarity from the dot determination. Here is the pictorial definition of a dot. You can see there is a dot. That means the current enters in that direction, the dot is there. So the polarity will be plus minus like this. The current will be entered like this in this position. Also you can see there is a dot here. So the current will be in that position. If the dot has been placed here, so the current will be in that position, the polarity will be changed. So that is the dot determination to find out the polarity of the current. And thank you very much for being with me in this lecture. I will give